In the next series of videos, I want to go over some of the principles of probability density transformation through an illustrated example. Specifically, if we have the mapping y equals arctangent of x, which satisfies a condition of being a monotonic function, we want to look at p sub y of y as determined, numerically with MATLAB, which is a quick and easy way of determining densities without having to do the analytical calculations. But we also want to use these numerical results to check our analytical findings of this from actually doing the density transformation. It's just kind of a neat way to compare what we analytically found against what we're numerically simulating, and that's relatively easy to do in MATLAB, so that's what we'll be doing. So here we are in MATLAB. Let's go ahead and decide how many runs we want to do, and I'm going to do 10 million runs for this example, 10 million samples, I should say, or draws of x. Let's say x start will begin at pi, and x end will be also at pi. So the way we specify or do our actual random draws from x is using the random function. We tell it what density we want to pull, in this case the uniform one. We tell it, and by the way, the subsequent arguments to the random function depend on what you enter for the density. In this case, it wants to know x start, x end, and how many draws to do. This will be a one row by n column vector that will go into our numerical x values. So we can just see that we can see what our values are here as far as the dimensions of x. Let me fix my format. So anyway, so at this point we can look at what the distribution of x looks like. So let's do that. Instead of figure, we'll do a histogram of x, and how many bins do we want to do? Let's define the number of bins to be basically the square root of how many x terms there are. I think this is a common convention. So we'll say figure, and we'll do a histogram of x in, and we'll do this many bins, and let's see what we get. Okay, so this is the figure we have, and this shows you kind of the of those 10 million runs. We see on the horizontal axis what the actual values of x are. On the vertical axis, we see what the counts, how many x values fell into that particular bin's extremes there. I should say how many x values fell into a particular bin where there are basically square root of 10 million different bins distributed from our x value. So this kind of verifies that we set up our input variable x according to the desired density. So at this point, what we want to do is set up a mapping between x and y. And so I'm going to do an anonymous function, f, and we'll call that arctangent. So f is again an anonymous function. I can say f of 0, and it will tell me the arctangent is 0, f of 0.5. So what we want to do is to establish values y in terms of these x values. Before I do that, I want to revisit this histogram plot and actually show how to do an estimate of the x probability density using the histogram. The y-axis here is in terms of counts, and so we basically want to scale this so that we have the relation, the relation, that p of x is normalized to 1, and we do that by basically in this histogram plot, instead of this vertical axis being in terms of counts, we basically make it so that this area is 1. And here's how you can do that. If I go back up to my terminal and I say, I'm going to use this histogram function again, but I'm going to make a call to it in a different way. I'm actually going to extract some output terms. So if I were just to plot this as is, what you end up finding is this plot here. Actually, I'm going to set my y limits to of this to roughly what they were for the previous one, so that we see the same, see them on the same scale. So this plot, this p of x that I just pulled out of the histogram is basically the values in the bins. That's what you see here. So with this, what we can actually do is, and by the way, the x values are the actual bin values. I want to make sure that it's clear. Xn was our samples that we pulled, and its size is going to be 10 million. The values of, or the length of x is corresponds to our bins that we chose, and it's going to basically just increase from here to here and be about the square root of 10 million in length. That's what we see. So to repeat, x does not is just indicating bin values. It is not a random drawn. It does not hold the random draw samples. But anyway, the way we normalize this p of x term is we just take it and divide it by times x2 minus x1. Actually, let me do this. I'll get back to this. We'll cut. I'm going to say dx equals x2 minus x1. So that's our spacing of our bins. And now I'm going to say px is set up such that it will have unit area. We'll see what that does here shortly. So if I say sum px times dx, it's unity. So if I were to plot this modified p of x, that's essentially what I see here. So I'm going to set my y-axis up where I can actually see this, and I'm going to label it as we see here, and that's basically a way to numerically get our density function p of x. At this point I want to return to this mapping, and so if I were to say yn equals f of xn, this takes those 10 million samples, this numerical samples of x, and puts them into our y function. So we can just do a quick histogram of, I'll just say 3,000 bins, and just qualitatively kind of see how our y histogram, or I should say density, how it qualitatively will appear. And let's actually do what we did with our previous result where we did we pulled out the densities and we find the dy value 2 by 2 minus y1 so that we can normalize this density dy, where now its integral is also 1. So we can take that and plot it. Plot y against py. Okay, so we get this figure, and let's just label him appropriately. So use this. Fix that. There we go. So that's a way of getting a numerical approximation to our density y. I say approximation because it is afflicted by sampling error, which with 10 million samples for this example, you can't really tell very clearly what those are, at least at this level of viewing. And so with this P of y, I just want to give some quick examples of how you can use that. First of all, you can find the mean value of y. Of course, we can just do our, the mean of our 10 million samples, and of course we get something very small as we'd expect. We can also calculate this mean using our density, and we do that with but before I type it, let me write down what that is, just as a kind of quick reminder. So the mean value of y, when we have its approximate density, will be given by this. Times y times dy over all y. And so that's the mean value, and the variance of y will be given by, I'll just say variance y. So the variance of y is the integral of y's density times y minus mean value of y squared dy. And of course that's what we typically refer to as sigma y squared. So numerically we can evaluate this equation according to the following. So we say in MATLAB sum of p sub y, we'll do a vector multiply y minus the mean value of y, and actually I think let me recalculate. I'm gonna cut this. Hold off on that. Let me just say mean y equals. So basically, I'm implementing this equation here. I say sum of py times y times dy, and I forgot to do my vector multiply. So I get that, and that should be pretty close to our statistical mean. And what I do next for the, just pasted what I had previously for my dot exponential. What I do next for my calculation of the variance will be somewhat similar form to that. So let's see if this works. Okay, there we go. So that's what we have for our variance in y. So we can do our analytical calculation get our closed form analytical expression, plot that on top of our simulated approximation to y's density, can make sure our analytical results agree with these, and then use these numerical calculations to corroborate what we find from using our analytical P of y and actually cranking out this type of integral. So that's just a quick way of being able to get a form, or at least a picture, of what P of y is without knowing, or I should say without having to do a analytical manipulation of the mapping between y and x to actually get that. So in short, it's a way to see P of y without having to know the equation for P of y.